Hello. In this video, we begin our unit on states of matter, and this is based on Chapter 10 in our textbook. In this unit, we are going to achieve the following goals. Number one, we're going to try to understand how states of matter differ from one another on the atomic and molecular level. We are going to try to understand how properties of a sample of matter depend upon the interparticle attractive forces. And we are going to try to understand what's going on during changes of state, that is, change from one physical state of matter to another, and deal with the energies associated with those changes of state. All of this is based on the 5 sections of Chapter 10. In Chapter 10.1, we're going to talk about the kinetic molecular theory of matter and gases. Then we'll talk about liquids, solids, changes of state, and finally the special properties of water. So that's the unit in a nutshell. So let us begin with the question, what are the 3 major states of matter? Well, this is something you learned back in elementary school. Of course, the 3 major states of matter are solid, liquid, and gas. And you may have discussed this previously, but we're going to talk in detail about how these states of matter differ from one another. Well, if you think about 3 different samples of matter, one is a solid, one is a liquid, one is a gas, and they are all at the same temperature and pressure, then they differ from one another based on the distances between the particles that make up that particular sample of matter. And that, in turn, is based on the strength of interparticle attractive forces. Now, back in our unit on chemical bonding, we talked about intermolecular attractive forces, and you may recall things like hydrogen bonding, dipole-dipole forces, London dispersion forces. We're going to go much more general now, because now we're talking about the strength of whatever forces there are between particles, whether they're molecules, atoms, or ions, that hold them together. Now, is there a model for how these physical states of matter differ? Well, of course, and you've seen it before. And here's a diagram I found on the internet. This is probably copyright violation, but we'll go with it. And we're looking here at taking a sample of matter at low energy and then gradually increasing the amount of energy that we add to that sample of matter. So at low energy, the sample of matter exists as a solid. And as you know, in a solid, the molecules or particles that make up the solid are arranged in regular repeating patterns, and they are held firmly in place, but those particles can vibrate within a limited area. As we increase the amount of energy in the sample, then the solid becomes a liquid. And in a liquid, the particles that make up a liquid flow easily around one another. They are kept from flying apart by attractive forces between them, and one of the properties of a liquid is that they assume the shape of their container. If we add more energy, then the liquid becomes a gas. And in a gas, the particles that make up a gas fly in all directions at great speeds. The particles are so far apart that the attractive forces between them are insignificant. We're going to talk about that in detail later. Now, if we continue to add energy, the next state of matter is plasma, but we're not really going to talk about plasma this year because that's really more physics than chemistry. So, let's begin with our first section of Chapter 10 on gases and the kinetic molecular theory. Now, we learned earlier in the year what a theory is. A theory is a model that we use to explain observed properties of the universe. And in this unit, we're going to be using a theory which is called the kinetic molecular theory of matter, sometimes abbreviated KMT. And this is a theory model that we're going to use to understand the properties of gases. There are 5 parts of the kinetic molecular theory, assumptions if you will, and these basically make up a model that we're going to use to explain why gases behave the way they do. So here are the 5 assumptions of the kinetic molecular theory, and yes, I do expect you to know these. Number 1, a gas is made up of a large number of tiny particles that are so far apart relative to their size that the actual volume of the gas particles is 0. Think about that. The particles are so spread out that the volume of the actual atom or molecule that makes up the gas is 0. Interesting. Number 2, collisions between the gas particles and the container walls are elastic. That is, when the gas particles bump up against the wall of the container or against one another, they do not lose any kinetic energy. This is an important part of the kinetic molecular theory, but we're not really going to be dealing with that too much this year. Number 3 is important. In our model, the gas particles are in continuous rapid random motion, and that's because they have kinetic energy. So the gas particles are constantly flying very rapidly in lots of directions. Number 4, there are absolutely no forces of attraction between the gas particles. They do not attract one another. And finally, the last assumption is that the temperature of a gas reflects the average kinetic energy of the particles. That is, as you increase the temperature of a sample of gas, the kinetic energy of the particles increases. Now, we're not going to be using this equation, but you can see from the formula written after that the kinetic energy of an object is proportional to the square of the velocity. What that means is that as the temperature of a sample of gas increases and the kinetic energy increases, the particles start moving faster. That's going to become important in our next unit. So now we're going to ask the question, how do we use this theory, the kinetic molecular theory of gases, to explain observed properties of gases? Properties of gases are kind of like natural laws. They're just descriptions of the way the universe behaves. And just like we did back in chapter 3, we're going to use our theory to explain why the universe behaves the way it does. So in the next couple of slides, I'm going to describe some properties of gases, and then we're going to answer the question, which part or parts of the kinetic molecular theory most directly explain that particular property. Okay? And several of these I'm going to demonstrate in class. So, our first property. Suppose we have a sample of gas trapped in one side of a container. There's a barrier and there's a vacuum on the other side of the barrier. What happens if we remove that barrier? Well, of course, the particles spread out to fill the empty space. That property is called expansion. Expansion is when a gas completely fills its container because the gas has no fixed volume or shape. So what part or parts of the kinetic molecular theory most directly explain why gases expand? Well, of course, one is because the gas particles are in continuous rapid motion. And the other part of the theory is that there are no attractive forces between the particles. Okay? If the particles are constantly moving and they're not attracted to each other, of course, they're going to spread out and the gas will fill the container. Oops. Here's our next property. Did I skip one? Nope, I'm on the right page. Suppose I have a sample of a gas that is in a container and the gas is denser than air, so it sits in the bottom of the container. Now suppose I tip the container over. Well, what will happen is that the gas will simply pour out as though it were a liquid. I will demonstrate this in class. It's pretty cool. This property is called fluidity. Okay? So one property of gases is that they are fluids. They can flow like a liquid. So once again, what part or parts of the kinetic molecular theory most directly explain why gases exhibit fluidity? Well, they're pretty much the same as the parts that explain expansion. That is, the particles are in continuous motion. And that there are no attractive forces between the particles. Because they're moving constantly and they're not attracted to each other, they can flow like a liquid. Suppose I have a container and I have a liquid in it. We can say it's water, but it could be any liquid. And then suppose I take a syringe that is filled with a gas and I inject a sample of gas into the bottom of the container. What will the gas do? Will the gas stay at the bottom? No. Obviously what's going to happen is that the gas is going to rise to the top of the container, and that is because gases have low densities. As a matter of fact, for a given substance, the gas is about 1,000 times less dense than the corresponding liquid or solid, of course, depending upon temperature and pressure. Well, which part or parts of the kinetic molecular theory best explain why gases have low density? You can go back and look at the list, but pretty obviously it is because the particles are far apart. Which means that for a given mass of gas, the volume is going to be very large. And because density is mass over volume, if the volume is large, the density is going to be very low. Here's another property. Suppose I have a sample of gas trapped in a cylinder with a piston on top. As you can see, the cylinder with a piston on top. And suppose I were to press down on the piston, and in doing so, increase the pressure on the sample of gas. What would happen to the volume? Well, of course, you might predict that as you increase the pressure, the volume decreases. And that is, in fact, what happens. Okay? This property is called compressibility. And I'll demonstrate this in class. The volume of a sample of gas decreases as the pressure on the sample of gas increases. So once again, I'll ask the question, which part or parts of the kinetic molecular theory most directly explain compressibility? That also would be because the particles are far apart from one another relative to their size. Now, if a gas consists of tiny particles and there's a huge amount of empty space between the particles, then it seems to make sense that if you simply increase the pressure on that sample, because the particles are so far apart to begin with, it's really not that difficult to get them a little bit closer together. And that explains why gases are compressible. The final two properties are called diffusion and effusion, and they're very similar to one another. In the top diagram, diffusion is very similar to expansion. When you remove the partition, the particles spread out to fill the container. Effusion is when you place a tiny pinhole in the partition, and the gas particles will eventually move through that tiny pinhole. But in both cases, these are explained by the parts that say the gas particles are in continuous motion, and also that there are no attractive forces between the particles. Once again, and you'll see that these two parts of the kinetic molecular theory explain most of the properties we're talking about, because according to our model, the particles are moving constantly and they are not attracted to one another. They can both diffuse and effuse. Now, all of this leads to the concept of what is called an ideal gas. An ideal gas is defined as a hypothetical gas that behaves exactly according to all parts of the kinetic molecular theory. So everything the kinetic molecular theory says about a gas, that is, that the particles actually have a volume of 0, that there are actually no attractive forces between the particles, and so on, that's what an ideal gas does. Now, you may have heard me express a little bit of skepticism about some of those parts of the kinetic molecular theory, and you might ask the question, do ideal gases actually exist? Well, the answer is no. Ideal gases do not actually exist. Real gases that we encounter in our day-to-day life and in the laboratory are instead referred to as real gases, and a real gas does not behave exactly according to the kinetic molecular theory. And that's okay. But it turns out that there are certain kinds of gases that are closer to an ideal gas. That is, they behave more ideally than others. So, thinking about the parts of the kinetic molecular theory, can you predict what kinds of gases would behave most ideally? Well, obviously, they would be gases that are made up of very small particles that have very, very weak interparticle attractive forces, which I'll abbreviate as IPAFs, okay? So if they are very small and have very weak interparticle attractive forces, that means they're not going to take up much volume, so their volume is going to be closer to 0, and there are going to be very, very weak attractive forces between them. Can you think of specific gases that would fit these criteria? Well, if you look at the periodic table, you'll probably realize that helium and hydrogen fit both of these criteria. And in fact, under pretty much any conditions, helium and hydrogen are considered the most ideal of the gases that exist. They are closest to the hypothetical gas described by the kinetic molecular theory. Now, the other question we can ask is, under what conditions will any gas behave most ideally? If we vary the conditions, we can make any gas closer to an ideal gas, that is, more closely fit the description of the kinetic molecular theory. Well, what conditions would that be? Well, if you think about it for a while, you'll realize that that would be when we are at conditions of high temperature and low pressure, because when we increase the temperature of a sample of gas and decrease the pressure, that means that the particles spread out. And when the particles spread out and are farther apart from one another, then they have weaker interparticle attractive forces, their volume is relatively less of the entire volume of the gas, and therefore they behave more closely to the kinetic molecular theory. Okay, in our next videos, we're going to talk about other states of matter and how they transform.